So definition, Gromov in 93, which is, we'll say that two groups, gamma and lambda, are measure equivalent which we'll abbreviate by ME, if they act in a commuting way, so we have an action of the product on some infinite measure space, say omega zeta, so this will be a, say, sigma finite measure space. And this is a measure preserving action. And such that, restricted to the action of gamma or lambda individually, this action is very simple. So we want that such that gamma and lambda individually have finite measure fundamental domains. So what this means is that if we look at just the action of gamma on this space, so the action of gamma on this space is very simple. It's just by choosing a fundamental domain, this is just like the action on some set direct product to gamma, where we just act by gamma leaves F alone, leaves it invariant, and then it acts on itself by just left translation. You don't get much simpler than this type of action for a measure preserving action. And similarly, for lambda acting on this measure space, it's also a very simple action from this perspective. So the interesting dynamics happens when you intertwine these two actions, so it's how they combine and they commute with each other. So Gromov introduced this because he viewed this as a measure theoretic counterpart to a theorem he could prove about quasi-isometries for groups. And there's some analogy between quasi-isometric groups and measure equivalent groups. So let me first give you some of the main examples. So one main example, main motivating example, is if we have gamma and lambda lattices in some G, which is locally compact. So then what can we do? We just set omega equal to G itself with Haar measure. So since there are lattices in a group, the group will be unimodular, so that if we look at the action of gamma on G from the left, and we look at the action of lambda on G from the right, well, then these will be commuting actions, so we can think of this as an action of the product. And the fact that you have a finite measure fundamental domain is more or less the definition of a lattice. So that these are discrete countable subsets and they have finite measure fundamental domains. So this is a nice example of a measure equivalence between these two groups. So the group G, the measure space G, implements this measure equivalence between these two groups. Another very nice example is that if we have an action of gamma on a space X, and this is a free probability measure preserving action, and we also have an action of lambda on a space Y, again, free probability measure preserving. And then suppose we have an isomorphism between X and Y, which preserves the orbits. So such that theta of a typical orbit of gamma is the same as an orbit of lambda. This is for almost every X. So this is called an orbit equivalence between the two actions. Well, in this case, you also get a measure equivalence between these two groups. In this case, you can set omega to be X direct product lambda. And how does lambda act on this? Well, lambda acts just on the right, acting on itself. So it's very trivial, and you see that it has a fundamental domain which is given by x. But how does gamma act on this? Well, the orbit equivalence gives you an isomorphism between this space and also y times gamma. And so the gamma acting over here is very trivial. It's the action of that. And so if you want to view the gamma action on this space, then you have to view it through a natural cocycle, the orbit equivalence cocycle coming from this. But you can verify that this gives you a measure equivalence. And moreover, conversely, if we have a measure equivalence, so if gamma is measure equivalent to lambda, so then they have free, maybe not quite orbit equivalence, but what's called stably orbit equivalent actions. So meaning you can restrict to positive measure subsets. And so I should also mention that one of the early developers of measure equivalence is Alex Furman, who's in the audience right now, I see. And he gave nice proofs of all these connections, and he has a fundamental paper developing these notions in the 90s. And in fact, so this in particular way, so one thing which is maybe not so obvious from this definition of Gromov is that measure equivalence is actually an equivalence relation, but this is true. So we have the theorem that ME is an equivalence relation. And in fact, there's a natural thing to do if you have two couplings. So this is, say, a gamma lambda coupling, and this is a lambda sigma coupling. Then there's a natural way you just take the product of gamma and lambda, and now, omega and omega prime, but now you have lambda acting on this space diagonally, and so you can quotient out by the lambda action. And since I had a fundamental domain, this is a nice quotient space, and this gives you a measure space on which gamma and sigma act. And you can show that this is, again, a measure equivalence coupling. So this is how you show transitivity, and the other properties are easy to show. All right, so let me talk about some invariants of measure equivalence. There's a number of invariants. So let me mention also names of people who proved that these are actually invariants. And a number of the other people. So some invariants of measure equivalence is amenability. In fact, due to the connection with the orbit equivalence, the Ornstein-Weiss theorem says, in fact, that there is a unique measure equivalence class containing all countably infinite amenable groups. So not only is it a measure equivalent invariance, but actually any two countably infinite amenable groups are measure equivalent. And if you're measure equivalent to any one of them, so the integers, then you're amenable yourself. So this equivalence relation doesn't distinguish amenability very well. On the other hand, property T is also a measure equivalence invariance. So this was first proved by Furman. And what else do we want to say? We also have the Hagerup property. And also the Caroline-Hagerup constant. So weak amenability. And also, due to Gaboriau, ratios of L2 Betty numbers. So I'm not going to talk too much about the definition of these, so let me not say anything more, but let me mention that as a consequence of this last fact, you see that in fact, if you take a free group with 2 generators, it is not measure equivalent to a free group on, say, countably number of generators. So here's a nice example of 2 groups which are not measure equivalents. There are also some fantastic rigidity results. Which I'll mention. The first is, I'll just mention 2. There are, of course, quite a lot by now. The first is due to Furman, where he looks at higher rank lattices. And the second I'll mention is due to Kita, where he studies mapping class groups. So in Furman, he essentially shows that if you have a measure equivalence between between a group, which is a higher rank lattice, and an abstract group, then that other abstract group had to be more or less a higher rank lattice itself, and the measure equivalence that you get actually had to come from the ambient Lie group, like the example I gave of 2 lattices in a Lie group. So this is a very powerful result. All right, so now let me switch gears a little bit and let me talk about von Neumann algebras for a moment. Since this is probably most of you have seen von Neumann algebras quite a bit, but I don't know everybody in the audience, so let me maybe give a very brief introduction to von Neumann algebras. So a von Neumann algebra is a star subalgebra of bounded operators on some Hilbert space, which contains, let me give it a name, about M, such that it contains the identity operator and is closed in the strong operator topology, which the strong operator topology is just the topology of pointwise convergence. So a net of operators converges to another operator if, when you apply it to each vector, it converges to that corresponding vector. So that's the definition of a von Neumann algebra. Some examples of von Neumann algebras is if M is, say, L infinity of some, say, sigma finite measure space. So then this is a von Neumann algebra where we view L infinity of a measure space as sitting inside of bounded operators on L2 of the measure space, where we view this sitting inside as multiplication operators, just pointwise multiplication. So if you have a essentially bounded function, you have an L2 function, you just multiply them pointwise, and that gives you another L2 function. And in this way, we realize this as a von Neumann subalgebra of this. So in fact, all abelian von Neumann algebras are of this form. So all abelian von Neumann algebras are of this form. So that von Neumann algebras can be thought of as kind of non-commutative measure theory. That's maybe the slogan for von Neumann algebras. The abelian von Neumann algebras, we get exactly the measure spaces, and so von Neumann algebras themselves are just measure spaces, but we dropped the commutativity assumption. Other examples, of course, B of H itself is a von Neumann algebra, and it also has a natural sort of measure, which we think of, so this is a semi-finite von Neumann algebra, and it has a measure, and the measure is given by the trace, which is just defined as take your favorite orthonormal basis and sum up these coefficients. This is Ci an orthonormal basis. So these are examples of von Neumann algebras, and it comes with this trace. If the Hilbert space is infinite dimensional, then this trace will give infinity to the identity, so it'll be more like a sigma finite measure space. This is how we should think of this. Then there's another example of von Neumann algebra, which will play a key role in my talk, and that is if we have a group, then we consider the group von Neumann algebra, and this is just going to be the completion in the strong operator topology of the group algebra, which sits inside of bounded operators on L2 of the group, where the group algebra acts on L2 just by left multiplication. So this is the group von Neumann algebra, and it also has a nice trace where we can define the trace of an element as just the multiply that element times the Dirac function at the identity and take the vector state corresponding to this state. So this is a trace, meaning that the trace of xy is always equal to the trace of yx, just like the usual trace for matrices or B of h that we have up here. Okay, so these are going to play a key role in my talk, these von Neumann algebras. And in fact, I'll give a definition. I'll say that gamma is W star equivalent to lambda if their von Neumann algebras are isomorphic. So this is obviously an equivalence relation on groups, and there's been a striking analogy with W star equivalence and measure equivalence. So let me maybe give you some invariance, and you'll see exactly the analogy. So let me put some names here. So we have Schwartz, Kahn, Jones, Chota, and Cowling and Agro. And then other people, many other people worked on this as well. Some invariants are amenability again. And in fact, just like the Ornstein-Weiss theorem, there's an analog for von Neumann algebras, and this is due to Kahn, where here you need to restrict to groups which have infinite conjugacy classes. That way you get trivial center for the von Neumann algebras. But you get that if gamma and lambda are amenable groups with infinite conjugacy class, so then you have that their group von Neumann algebras are isomorphic to each other. So these are countably infinite groups. So again, any two amenable groups, countably infinite amenable groups, as long as they're ICC, they give rise to the same von Neumann algebra. And conversely, if you're isomorphic to a von Neumann algebra of an amenable group, then you're amenable yourself. So that's a result of Schwartz. Other invariants, we also have property T. So this is a result of Kahn and Jones. And we have the Hegera property. So this is due to Chota. And we also have the Cowling-Hegera constant, which is due to Cowling and Hegera. So let me mention, so one thing I should mention right away is that you notice that it's those very similar results that I had on the previous slide, where we have a lot of the same invariants, and indeed there's a nice analogy between these two notions of equivalence. But you'll notice also that the names of the people who prove their invariants are almost completely disjoint. So we have these two kind of separate theories which have a lot in common, and a lot of the proofs have a similar feel to them, but somehow they're completely separate proofs and they require different techniques. Which is always something that seemed very curious. Not all techniques translate from one category to the other. So for instance, The ratio of L2 Betty numbers, whether they're an invariant of W star equivalence, is a well-known problem. And this is related to the free group factor problem. Which goes back at least 60, 70 years or so, which asks if you have a free group on two generators, is this isomorphic to a free group factor coming from countably infinite generators? So this, in other words, is F2 and F infinity W star equivalent. So this is still an open problem. And also another well-known open problem is Kahn's rigidity conjecture. Which asks if this higher rank rigidity phenomenon that Furman proved for measure equivalence, if this also holds for W star equivalence. So here we have gamma and G a higher rank simple Lie group, and gamma a lattice. And if L gamma is isomorphic to L lambda, does this imply that actually gamma is isomorphic to lambda? So unlike measure equivalence, the group G itself doesn't give a natural W star equivalence to the two lattices. So the conjecture is even that two lattices in the same Lie group should be non-isomorphic unless they're isomorphic lattices. So this is also, this is a well-known open problem, which has also been open now for about 40 years or so. And there's no single example where this is known to hold. Although Kahn did conjecture a more general thing, which was about all property T groups. He conjectured this, although he's motivated mainly by this example. But there are now examples, even coming out earlier this year, of property T groups which satisfy this implication. So there are now property T groups examples, which is nice. Okay. So now I want to introduce one third notion of equivalence, and this is the new notion in the title of the talk. So this is definition. This is due to Ishan, myself, and Lauren Ruth. And it's as follows. So we say that gamma and lambda are von Neumann equivalent. And we'll write gamma lambda if. So what I'm going to do is I'm going to take the definition for measure equivalence, and I'm just going to make that measure space non-commutative. So it's not a very difficult definition. So if there exists commuting actions, gamma, and I'll think of one acting on the left and one acting on the right, so I'll write it like this. So, or if you like, you can think of this as an action of the product group on M, but now M, I'm not assuming here is L infinity of some measure space, but I'm allowing it to be any von Neumann algebra with a semi-finite trace. Commuting actions, these are trace preserving actions. So this is where M with its trace is a semi-finite von Neumann algebra. And this is such that I want in some way to say that the action of gamma is trivial, or something to say a fundamental domain. So that's exactly the definition, and then I'll explain what I mean by a fundamental domain, such that gamma and lambda each have a finite trace fundamental domain. And what is that? So I just mean that there exists some projection in M, we think of this as the characteristic function of a fundamental domain. In the commutative case, there exists a projection such that if we look at all the translates of this projection by the gamma action, this should be a partition of identity. So if we take the sum over all t and gamma of t times this p, this should be the identity in M. So if you take your commutative definition and you think of a fundamental domain there, and then you take the characteristic function of that fundamental domain, that will exactly be a projection in L infinity, which has this property. So this is exactly the notion, this is a straightforward generalization of the notion in the commutative case. And then again, similarly, for the lambda action on M, we want another fundamental domain there. And we want this, of course, to be a finite trace fundamental domain. So that's the definition. Any questions about the definition? I take from your silence that everybody's very happy with the definition, or at least everyone has fallen asleep. It's hard to tell when you give a Zoom talk. Okay, so let me move on and give you some examples. So examples, well, I already mentioned that if you have gamma is measure equivalence to a group lambda, so then there's some measure equivalence coupling, omega zeta. And of course, we then have the corresponding dual action on the L infinity space. And this is a von Neumann equivalence coupling in the sense that I gave you. So, so that we can naturally get that gamma and lambda are von Neumann equivalent. So that's a straightforward example. What's perhaps a bit surprising at first is that the notion of W star equivalence also fits into this picture. So if gamma is W star equivalent to lambda, so if they have isomorphic von Neumann algebras, so then what can we do? Well, the isomorphism of L gamma with L lambda means that we can identify these two spaces, L2 of gamma, let me just write equals because I'm gonna think of them as being equal to each other. We can identify them in such a way such that L gamma is identified with L lambda under this isomorphism. So what does that mean? That means that I can just set this to be my script M and the trace to be the standard trace for B of H that I already mentioned earlier. And now we have two actions which we can act on here. So the gamma action on M on B of L2 of gamma is acting by conjugation by the left regular representation. So this is by gamma times an operator T is just going to be lambda gamma T and the gamma star. So this is just conjugating with the left regular representation. But on the other hand, the lambda action on B of L2 of lambda, now we'll think of it, but we're identifying these two spaces, will be not by conjugating by the left regular representation, but by conjugating by the right regular representation. And now the point here is that the isomorphism allows us to identify L gamma and L lambda, which means that the right regular representation will commute with anything in L gamma. So in particular, commute with the left regular representation coming from gamma. So that these two actions do indeed commute with each other and give us an action of the product on the space. Moreover, if we let P denote the projection onto the one-dimensional subspace, which is spanned by the Dirac function at the identity, well, then you can compute exactly what is gamma times P. Well, it's conjugation by this, and so this will be the projection onto the one-dimensional subspace spanned by delta at that gamma. which means that in particular, it's orthogonal to P, and it's their pairwise orthogonal for different gammas. And if you sum up overall, say T and gamma of T times P, you just get the sum of all these rank 1 orthogonal projections, but they form a basis for L2 gamma, and so you get that this is the identity. And similarly, if you take the same projection, you can also think of this as the projection onto delta E and lambda, and the same projection, you also have the same thing in lambda. Yes. So in this case, they both have a fundamental domain. In fact, it's the same fundamental domain, and it also is finite trace because it's a rank 1 projection, so its trace is just equal to 1. So the trace. So this gives a W star or a von Neumann equivalence between these two groups as well. Yeah, what else do I want to say about that? Yeah, let me mention this result of Kifan and Ioana from 2011. I see there's a question. Do you have a good example where the coupling algebra is not type 1? Yes, I do. And in fact, so maybe let me do that example as well, although I won't get a proof. So another example is if you have not just, so here I did W star equivalence, but you could also do virtual W star equivalence. So gamma is virtually W star equivalent to lambda. So this is a notion introduced by Polpa. And that's if L gamma is isomorphic to a finite index von Neumann subalgebra of some amplification of L lambda and vice versa. So actually this allows for amplifications and passing a finite index. So this is maybe a bit more directly analogous to measure equivalence right here. And the fact is you can take this example and you can show that if you have virtual W star equivalence, that also implies that they're von Neumann equivalence in this setting. However, the coupling you take, if this index here, so if this T is an irrational number, then you can't do this with a type 1 von Neumann algebra. You have to do it with something else. So this is the coupling is not type 1 if T is not a rational number. So that's a good example to think about. Yeah. Although you still can do it with an injective von Neumann algebra in that case. And indeed, I think it's an interesting question if you could also define the notion of von Neumann equivalence with injective couplings, and I don't know if that's the same as von Neumann equivalence in general. All right, so I should mention that maybe a proposition, and that is that this is indeed equivalence relation. So von Neumann equivalence is an equivalence relation. And the proof is almost the same as the proof I've already given before. So the proof is you just have, if you have a von Neumann equivalence between gamma and lambda, and you have another von Neumann equivalence between lambda and sigma, then you just take their tensor product, their von Neumann tensor product, and now you have lambda acts diagonally here, and so you look at the fixed, the von Neumann algebra of fixed points for this, and now you have that gamma, of course, acts here by just acting on M, and sigma acts here by acting on N, and then you have to do a little bit of work to show that this has a natural semi-finite trace. You only have to do a little bit of work. Of course, you have a tensor product here. It has a natural semi-finite trace, but when you restrict to the lambda invariant things, this may have all the projections there may have trace infinity. So you have to take not just the restriction of the trace, but you have to define a new trace. But this is possible to do, just like in the abelian case. Let me mention another result. So this is what I started to mention. This is due to Kifan and Ioana. And this is from 2011, where they showed that if you take the integers, free product, the integers, direct product F2, that this is measure equivalent to the integers. And now here we put the infinite symmetric group, direct product F2. But on the other hand, if you take the same two groups, so these two groups are ICC, that's an easy thing to check, and they are not W star equivalent. So this is a nice example to think about, and there are other examples of this type of phenomenon as well. So in particular, since these are measure equivalents, they're von Neumann equivalents, so we see that von Neumann equivalence is definitely different than W star equivalence. However, I don't have any examples where like the converse of this holds, so I actually don't know. It's still open is if von Neumann equivalence is the same as a measure equivalence. So that's still open. I have no counterexamples to that. Of course, proving that they were the same would be, amazing. And all these rigidity results, all these questions, cons rigidity conjecture, free group factor problem, and everything would just follow immediately. So certainly they're not the same equivalence relations, but I don't know of a counterexample. So that's something to think about. So now let me mention maybe, so let me mention one theorem which we're able to do. So again, this is Ishan, myself, and Lauren Ruth, which is that amenability property T, Hager property, are all von Neumann equivalence invariants. So of course, we already know this in the two separate categories. So this is not perhaps surprising, but the nice thing about this is that this gives a unified proof, which then works in both settings. So we had these two disjoint theories, which showed all these invariants. And so it's nice, I think now we have a connection. We see why these theories are in fact similar. It's because they're both follow from a more general result. And there's a common proof which generalizes all of these things. Specifically, there's a general procedure to induce a representation from one group to another via a von Neumann equivalence. And then you can show that things like weak containment, mixing, and these sorts of properties are preserved under this induction. So that's one thing which is nice. But I should mention, of course, why we were interested in this notion of von Neumann equivalence. This is not the project we started on. In fact, the idea that you could take the definition and just make it non-commutative kind of surprised us. This is not what we were aiming at originally. What we were aiming at is a different property of groups and studying that different property in the vicinity of measure equivalence. So let me give you that right now. So this was a definition which was introduced by Remy Boutonnet.
Oh, Jesse?
Yes.
Still in the invariance section.
Yes.
Did you try stability under free products or something? Is that?
So I think there's a lot of questions to think about. Stability under free products, I think probably should work, but we did not do that. Also, you notice I didn't put Cowling-Hagerup constant there. I don't think that's because it's a difficult result, but it's just that we just didn't do it. We already had enough in the paper, so we just didn't do it. So hopefully one of my students will do it. At least I told them they should, but we'll see. On the other hand, yeah, stability under free products is something we thought about briefly, but I didn't see any obvious obstruction to it, but the direct proof, adapting the direct proof from measure equivalence didn't work. So I think it would take a little bit of work to figure that out, but maybe, probably that goes through. Yeah, of course, one of the main things that we thought about was, of course, if there was a way to adapt the higher rank rigidity phenomenon or something like this in this setting. And I think one of the things which looks excited about this approach is that in order to achieve higher rank rigidity for measure equivalence, you need to work with like Zimmer cocycles, and you need to be able, you can encode the Zimmer cocycles in the measure equivalence coupling. And so now that we have never had a notion of a cocycle from a von Neumann algebra before, and this was one of the main obstructions of how to try to generalize this rigidity, but now we have this non-commutative measure coupling, and that can allow us to take the role of the cocycle in Zimmer's superrigidity theorem. So at least now there's at least, I think, a framework of which to try to prove higher rank rigidity in the von Neumann algebra setting. So I think this is the proper framework for that. Unfortunately, trying to take your proof, Alex, and to adapt it into this framework, there's a lot of other things that need to be adapted as well, and that's where there's still some major difficulties in figuring out those. So I think we're still pretty far away from, say, proving Zimmer style superrigidity, but I think this is the right framework to study it at least. Okay, so that was a bit more than what you were asking. Other things, so yeah, other properties we thought about as well. So of course, L2 Betty numbers, but I think that seems just as hopeless as Connor-Shlechtenko's approach. I think if all the difficulties in Connor-Shlechtenko's approach show up as soon as you're dealing with something non-commutative. There's also bounded cohomology of mono-shalom. Now there, I think there's some potential there, and that is something I'm currently thinking about, but it's still very too early to say anything for sure. Okay. I think those are all the things we thought about those. So if you have other ideas, I'm interested as well. But let me mention the other property, which was kind of what led us to this framework here. And that was a property introduced by Remy Boutonnet, Adrian, Ioana, and myself a couple years ago. And that's the following. So we'll say that gamma is properly proximal if, well, what do we want to say? We want to say it's like a form of non-amenability. So it's a strong form of non-amenability. We want that there does not exist a left gamma invariant state on, well, if we just took L infinity, that would be amenability. So what we're going to do is we're going to quotient by the C0 functions. Well, this again would still be non-amenability, but now what we're going to do is we're going to look at the right invariant functions here. So we look at, so of course gamma acts on the left and the right. So here we look at the right invariant functions. So now this gives us a much smaller subspace of the whole space. So having a left invariant state here would be theoretically weaker than amenability, and indeed it is. So this is the definition that we have here. We were interested in this because we have non-commutative, so we have rigidity applications for the von Neumann algebras for L gamma if gamma is properly proximal. So specifically, we could show, for instance, that L gamma doesn't have a weakly compact Cartan subalgebra, if you know what that is, and things like this. So this is why we were interested in this notion, why we developed it. Let me give you some examples of groups. And the nice thing is that with this notion, there are a lot of examples. So specifically, we have non-elementary hyperbolic groups. And we also have even relative hyperbolic groups. I see there's a question. How is this definition related to the usual notion of proximality in dynamical systems? Yeah, so the terminology is derived from there. I think for the sake of time, maybe I won't say the reason is because there's another equivalent definition. So this is the concise and easy definition, but this is not actually the definition that you use. So this is the definition you use for applications, but to actually show something is properly proximal, I use a different definition, and that's related to dynamics, and there's a certain amount of proximality involved in the dynamics. So that's maybe all I'll say about that. After the talk, I'm happy to be a bit more specific on that. But in particular, using the dynamics of the Gromov boundary, you can show that non-elementary hyperbolic groups are properly proximal. You can also see that in general, convergence groups are another nice examples. But also, you also have non-amenable bi-exact groups. So for instance, like Z2 cross SL2Z, or like Z wreath product F2. These are examples of groups which are non-amenable bi-exact groups, but they're very far from being convergence groups or relatively hyperbolic. On the other hand, we were also able to show that lattices in non-compact semi-simple Lie groups. So this is for rank 1, like hyperbolic type properties, but also for higher rank as well, we get the same properties. So for instance, things like SL3Z are also properly proximal in our sense. We can also show that this property is stable under extensions. So in particular, under direct products, finite direct products, it's stable. And then one other result I'll mention, this is a recent result due to Horbes, Huang, and Lacroix. So just from maybe a month or two ago, that many mapping class groups and many cat0 groups are also properly proximal in this sense. So this is, there are a large number of groups which satisfy this. For a non-example, we have that interamenable groups are not properly proximal. Basically the same reason I told you before, so this you can see directly from the definition, because if you had a left invariant mean, so if you had an amenable group, then of course you would have a left invariant state on any C-star algebra that you're acting on. But here, since we've quotiented out by the right, since we're looking at only the right invariant functions on this quotient space, the conjugation action is the same as the left action. So if you even have a conjugation invariant mean on L infinity, then in particular you have a left invariant mean when you quotient it, when you restrict it to the right invariant functions, and hence you're not properly proximal. So interamenable groups are not properly proximal. Now, this relates to our project in that we have the following theorem. So this is, again, 2S3, which is that proper proximality is a von Neumann equivalence invariant. So in particular, as a corollary, it's also a W star equivalence invariant and a measure equivalence invariant. And that was our original goal, was to show that this was a measure equivalence invariant. So kind of how the project started is we wanted to show that the proper proximality was a measure equivalence invariant, and we were able to do that. And then we also want to show that it was a W star equivalence invariant, and we were able to do that with a completely separate proof. And this really bothered us for a while. Why we had two completely separate proofs for these two things? Like there didn't seem like there were any similarities, and so that's why we felt that there must be some unifying framework of where to do this. And this is where the notion of von Neumann equivalence actually developed, was finding this common framework for these two proofs. And I'll mention briefly a bit on the techniques that go into this. And it's actually very similar to showing that Hegel property or property T immutability are also invariants, is that not only can you induce a unitary representation from one group to another, but you can induce a Banach space representation from one group to the other. And now you can rephrase this definition of proper proximality in terms of certain fixed point actions for Banach space, for actions on Banach spaces. So mainly just like, or non-fixed points. So just like immutability, one way to say it is there's an invariant mean on L infinity. Immutability is also equivalent to every action on a compact convex subset of a dual Banach space has a fixed point. And you can also take the definition of proper proximality or non-proper proximality and phrase this also in terms of fixed points for certain classes of dual Banach space. Not all of them, but for a certain class. And this class we were able to show, when you induce it from one to the other, stays in this class. So that's roughly the idea of where this came from. So the one nice corollary of this, let me give you an example due to Capras. From 2018. And that is that if you look at SLDZ and let this act on Z adjoin 1 over P to the D. And now you look at also SLDZ, let this act on Z to the D in the natural way, and then take the direct product with QP mod ZP to the D. So what Capras showed is that these two groups are measure equivalent, because in fact these two groups are both lattices inside of a common locally compact group. And so these two groups are measure equivalents, but because you have property T for SLDZ here, you have the action here, and so this is an example of a group which is not interamenable. On the other hand, this group right here is a direct product with an abelian group, so this group is interamenable. So as a corollary of our theorem above is that this group right here is an example, so this is not interamenable, and it's not properly proximal. So there was maybe some initial hope or something, some thought that maybe proper proximality was just non-interamenability. But this example now shows that it's actually a more complicated notion, this notion of proper proximality. And yeah, I think there are some potentially interesting things coming out of that. Then let me just finish by mentioning, so of course, this shows that in particular, proper proximality is a W star invariant. And so there should be some notion of what it means for a von Neumann algebra to be properly proximal. And so I should say that that's joint work with Cheng Ding and Srivastav Kunawal Kam Hilavali. These are two students of mine, and we are able to define proper proximality for von Neumann algebras. So there's a natural notion. This notion can be translated in the language of von Neumann algebras to give a complete, to give a proper setting there. And this gives a new proof of at least the W star equivalence, because we show that a group has it if and only if its von Neumann algebra has it. But this is work in progress, and hopefully by the end of summer we'll have this. So let me go ahead and stop right here, and thank you for your attention.
Thanks, Jesse. Any questions? I think there is something in the chat going on. Ben has a question.
I think I answered Ben's question when he asked it.
Right.
May I also ask a question?
Of course.
The first question was, so do you know that groups with first L2 beta numbers are properly proximal? Something
I
like
don't,
this?
I suspect not, but I don't know. Yeah. So there's a few classes.
You suspect that there is a counterexample, or you suspect that this is true?
I don't know. Okay.
Okay.
I don't know. I mean, I suspect that there are groups with positive first L2 beta number which are not properly proximal. That's what I suspect.
Okay.
But I don't know. I don't know an example or anything like that.
Okay.
Yeah. So classes of groups which we don't know. So the class of groups are, yeah, groups maybe if you have positive first L2 beta number, then we don't know if this implies proper proximality. Say ICC property T groups. This we also don't know if this implies proper proximality. My thinking here is I think that this also should not imply in general. So of course, if we have a property T group with infinite center, then it's interamenable and hence not properly proximal. But if you have ICC property T groups, then I don't know. Yeah, it would be nice if there were an ICC property T group which was measure equivalent to a property T group with infinite center. I don't know if that's possible or not. Another class of examples we don't know is acylindrically hyperbolic groups.
That was my next question. Is.
Yeah, this is also a class of groups which, yeah, so in all three of these, we know there are many examples which are properly proximal, but we don't know if they all
Um,
I have also one question. Could it be possible that, for example, groups with non-trivial second bounded cohomology are properly proximal, whatever, with L2 coefficients? I mean.
Yeah, that could be. So I think
because I just meant that many of your examples, they have in some sense negative curvature, and I was just wondering.
C-reg,
could
D-reg,
it be?
These are also unclear. Yeah, it could be possible. No. So I think the problem is that so groups with non-trivial second boundary cohomology in the left regular representation, the only examples I know come from spaces which have very strong like north-south dynamics, and this is also the same type of phenomenon that gives you properly proximal. So I don't know if that's just a coincidence that we can just prove that for those classes of groups, or if there's some underlying reason for that. My feeling is that I think that this is more or less a coincidence, and these are just the techniques we have.
Okay.
Because I feel like these properties should be pretty different. but I don't actually know.
Okay. And one more question. I'm sorry, so many questions. I know that convergence groups are properly proximal. Do you know if? And I know also that there is a Bowditch proof that like Bowditch classification, characterization of convergence group, that it's acts properly discontinuous on triples or something like this.
Mm-hmm.
Do you know if it's possible to see the, like, if I forgot the old definition of convergence group, can I see directly from Bowditch definition properly proximality? So I mean by action on triples. So
can you see directly from the action on triples that the group is properly proximal? I mean, yeah. So I mean, I guess knowing that the action on distinct triples is properly discontinuous, to show that that implies the usual definition of a convergence group is pretty.
Yeah, I just, yes.
Yeah, that direction is easy. So in that sense, from the triple definition to get proper proximality, yeah, it's pretty easy, just because you can go through the other one. It's the converse. It's the converse that's difficult.
Okay. Yeah. Thank you.
Sure.
More questions?
I can maybe say briefly why convergence groups are properly proximal, because that's maybe gives a big hint on how to do all this stuff. And that is that, of course, convergence groups are by definition, they're spaces which act on a compact Hausdorff space. And you have that there is the action on the distinct triples is properly discontinuous. So another way to say that is that if, and this is the only thing you need to show proper proximality, is if you have any probability measure, and this is say without invariant measure, this convergence action. So one way to say the property we use from convergence action is that if you take any probability measure which is diffuse, so then it has the property that if you take any sequence of elements in your group and you start pushing this forward, well, since the sequence kind of pushes everything to a point or 2 points, but since it's diffuse, it's just going to push it to 1 point. So that means that if you took a translate of this, and then you took the same sequence, that these will converge to the same probability measure weak star. So you have that this converges weak star to 0. So this is the property, and this we felt like was a sort of proximality. You're kind of pushing points together, but it's for any sequence. So this is whenever gamma n goes to infinity. So that's why the properness. So it's like a proximality property, but it's also properness for any sequence. You get this proximality. And from this, so what you can do from this is you can naturally define this map from C of k to L infinity of gamma modulo C naught gamma under the gamma right translation by just taking a function and sending it to the function, which I'll tell you what it is. It's an L infinity function. It sends it to this f tilde, which at t is exactly the integral of f d t eta. And this property, which I've given you up here, exactly says that it maps into this target space here. So if you were not properly proximal, then you take your state here, you could pull it back to an invariant measure here. But by definition, there's no invariant measure, and hence there's no invariant state. So that's the proof of why convergence groups. And this is why we call it properly proximal, because it's all about the action on this space K. All right, Alan, you had a question?
Yeah, it was about Kahn's rigidity conjecture. Did you say that it was checked for some property T group?
Yeah, so earlier, like this year, maybe a month or two ago, there's Yunutsky Fan and Cyril Houdaye and I think Sayan Das and my student.
Krishnendu.
Yes, Krishnendu was the fourth author. So Krishnendu Khan. So they put out a paper where they give examples of property T groups which are W star super rigid. But these groups are definitely not lattices and higher rank V groups. So that part is still wide open.
Okay, so I missed that.
Yeah, it's on the archive. I think they put it up like 2 or 3 months ago, or maybe 4. So, yeah.
It's not the paper where they prove that trivial fundamental group. It's a different paper.
I think they have 2 papers. So trivial fundamental group. Okay, so I should say I might be confused and maybe I'm saying something wrong. But no. I believe there are 2 papers. One, which is just by Krishnendu and Sayan and Yanutz, where they give examples with trivial fundamental group. And then I think another one with Surreal, where they give examples of W star superrigid. But I mean, I could be misremembering. So there are definitely 2 papers though, so you can look and see exactly what they prove.
Okay.
More questions? All right, let's thank Jesse again.
All right, thank you.
Thanks, great talk.
Great talk, thank you.
Thank you.
Jesse, I think you are the only one who can end this session because you are host right now.
Okay. All right, well, I'll go ahead and end it then. So it's nice to see everybody. And hopefully get to see you all soon in person when this whole thing is over.
Good to see you, Jesse.
Yeah, good to see you.
Nice to see you.